All right, guys, let's take a look. My mask wants to live in my eyeballs. Okay. Yeah. So I'm not going to take a derivative here first. I'm going to rewrite parts of it. This needs to be pretty quick. Rewriting roots. It's x to the power divided by the root. Anything on the bottom becomes a negative power when I move it up top. Okay, I like it. And then I can take a derivative, because now they're all the same rule. They're all the power rule. So 3/5 times 2 is 6/5 x to the negative 2/5. And this will be negative 3 times negative 3 is 9. Go down by 1 is negative 4. And I've left no room for the next problem. Yay! Yes? Maybe? So it's all about, if you can simplify the function to match a rule correctly, or if you can simplify a function and make some shit disappear, of course do that. Because then there's less to worry about with the derivative. Alright, this guy shouldn't be too crazy. This is just what rule? Yeah, this is just product rule. Is that cool? Let me see if I can sneak it in here. Derivative of the first times the second plus the first. What's the derivative of cosine? Negative sine. So then I end up with 3 theta squared cosine theta minus theta cubed sine theta. And now I have no room for the next one. Okay, I like it. Is that all right? Can you guys see that all right? It got all slammed in there. That wasn't too bad, right? That was like, oh, thank God, there's no chain rule, because the inside's just theta. Ooh, okay. What about C? What rule do I use, or can I use? Yeah, you could actually never have to use quotient rule ever. Are you curious about that?
Wouldn't you just put 2x plus 3 to the negative 1?
Yeah, you just bring the 2x plus 3 up, be to a negative 1 power. Then it's a product rule, right? If you want to. I will tell you this, they're both about the same in the end. Yeah. Just do quotients, fine. So G prime, you've left yourself no room, Jeff. I'm going to do this kind of quickly. The derivative of the top stays the same, times the bottom, minus the top. What's the derivative of the bottom? 2. All over the bottom squared. There's really not a ton I can do with that. Normally we want to factor stuff. So let me see if you guys can handle this. If I take a 3e to the x out, it'd be 2x plus 3 minus 2. Did you have to do what I did? No. But normally we want to factor stuff. But if you guys distributed and then got your like terms together, that's fine too. Is everybody all right? You guys okay? I see concerned eyeballs above some people's masks. Yes?
Yeah, how does that, like, where does the, because I did 3e to the x times 2, so I did the 6e to the x that we talked about.
Sure.
So where does that go?
Look, here, look. 6e to the x. 6xe to the x, yes? If I distribute that, so.
Yeah, but then what happens to the normal e?
To the what now?
What happens to the one that's in front, the 3e to the x?
That's the one when you distribute.
Yeah. Okay.
Oh, then it just stands. Okay.
You gotta trust me.
Got it.
Okay. All right, now. Okay. What about D?
0.
Hell yeah. So no dependence on any variables here. So it's a constant.
Yeah, that's what I thought.
What is the constant? I don't care because I'm taking the derivative, it goes to 0. This one is kind of gross, and we actually learned this derivative before we learned e, because that's when we went, oh, if I put an e there, it's itself. That's the one base for an exponential that is its own derivative. So how does this work? It works very similar to e. Derivative of 5 to the something is 5 to the thing times natural log of 5. That's a little adjustment because it's not e. Then, of course, I got to multiply by what?
Derivative of the inside.
Derivative. Okay. Sorry. I understand. We're all tired. Whoa, shit. That is really zoomed in. I really want that to make sense. I desperately, obviously, always want things to make sense. This is one rule. This is the rule for something to a power, right? A constant to a functional power. That's the rule. Then the inside gets a turn. So general don't care how freaky the rule is for the outside. It just says, I get a turn, I get a turn, I come at the end, right? This is a little bit funky. It gives a shit. I still got to do the inside derivative. And of course, there I get derivative of this is 2x minus 3. So I'm just going to throw that out front. I could have thrown the natural log of 5 out front. Who cares? Okay. If you put an e here instead, doesn't this part go away? It's exactly the same rule, really. This one should be nice, right? What do I assume a is? Why can I do that? Because this is a function of x, so a must be a constant. So h prime, what's the derivative of cosecant? Negative cosecant stuff. Cotangent stuff. And the derivative, what the derivative of the inside is a. I'm just going to throw that out front. So that was the derivative of the inside right there. Negative cosecant cotangent of stuff. And the inside's derivative is a. I like it. Yes?
Can you write it as negative a cosecant cotangent of a of x?
No.
No,
Because cosecant cotangent is not a function.
Oh, it's cosecant x. Cotangent.
Yeah, cosecant doesn't make any sense unless there's something in it. Right? Okay. Just like if I just had a square root with nothing inside of it. Wouldn't they be like, what the hell? Square root of what? Okay, so be careful. That's why that sucks. I understand there's more writing than normal, but oh well. We all have to deal with it. You guys are all antsy because I normally let you out early. It's too bad. What about this guy? This guy's quick, right? 0. Okay. This guy.
I thought it was negative 2.
What? What?
There's no variable.
Yeah, it's cosine
there's
is 2 is a
no
number.
X in it. Okay,
No x
okay,
in it.
got
No
it.
variable dependence at all. Yeah. Real quick, by the way. All right, please never do this. But what's the derivative of cosine, sine of thing times the derivative of 2, because that's what's inside, and what's the derivative of 2? 0. So that's why it comes out to be 0 in the end. So, but I never have to do that, right? It's any number, the derivative is 0. Cosine of 2 is a number. That's all it is. It doesn't change. So its rate of change is 0. Watch this. Done. All right. You guys are like, you can't watch it, Jeff. You're too zoomed in. All right, so don't. Remember with the limits, what did we do with limits? Did we try to throw the number in first before we did shit? Remember that? Because then that's easy. So what do I do with functions before I take a derivative? I see if I can simplify it at all. Good Lord, yes. Okay, so if you do the quotient rule, you do eventually get here if you simplify it correctly. But man, that's much more work than you have to do. And then this guy, oh shit, Jeff, why a secant? All right. What's the derivative of secant? Secant something, tangent something, and I left myself no room at all, times the derivative of something. Thank you. Derivative, Jeff. Oh, geez. I got no room over there. You got a whole other sheet of paper, Jeff. Well, that's true. All right. Let me write that again. So secant something. Yeah, Jeff, you give yourself so much more room. Tangent something times the derivative of something. I do. I totally do. I just do. Look at all this room I could have put that in. Jeez. All right. Is everybody cool? Here's what the derivative of secant is. Kabam. times the inside's derivative, yes? So now that's what I focus on. Look at Jeff, sort of learning, almost learning. Not really learning a lot, but oh well, too bad, Jeff. What's the derivative of e to the sine beta? E to the sine beta times the derivative of sine beta, which is just cosine beta. Okay. And of course, you could bring the cosine beta out front and the e to the sine beta out front. Okay. Sorry? So, derivative of e to the sine beta is e to the thing times the derivative of the thing. And the derivative of sine is cosine. So the derivative of e to the sine beta, yeah, the outside function is e, inside function is sine, so its derivative is cosine. I like it.
Can we just pull cosine in front?
Sorry?
Can we just pull cosine?
Yeah, you could pull the cosine and the e out front. Okay. I don't care. You can do it. Now, this little freaky dude. This kind of sucks. The notation we use, this is actually this, and this is what threw people off. That is what that means, yes? So the inside function is tangent. So let me kind of do this a little bit quickly. I did want to sort of, it's too bad, Jeff. So the 2 comes down, tangent pi x, to the first power now, times the derivative of tangent pi x. We stop for a minute. Right, the 2 comes down, is to a first power now, times the derivative of the tangent that's inside the square. Okay. 2 tangent pi x. Derivative of tangent is secant squared pi x times the derivative of pi x. So I'm just going to throw a pi out here. Is that cool? I don't know if you guys are cool with that. Derivative of the inside. Yeah, go away. Derivative of the inside is pi. That's over here. Where do I want to know the slope? For what x value? 3/4. Yeah, so I'm going to throw a 3. This is the slope function. It tells me the slope at any value of x. What's tangent of 3/4 pi? Tangent of 3 pi over 4. I'm going to throw a 3/4 in for x. Is that cool? What's tangent of 3 pi over 4? Negative 1. So far I got negative 2 pi. Is that cool, everybody? Tangent of 3 pi over 4 is negative 1. What's secant of 3 pi over 4? Oh, shit.
How am I going to know you looking at my unit circle?
All right, I'll just tell you. It's negative root 2. And then it's squared. Negative 2. So this guy's slope is 4 pi. Isn't that a fantastic slope? If you don't believe me, you can check me out on that secant, but. All right. This guy's slope is 4 pi. So this is a really good place just to throw shit into there. So y minus 1 equals 4 pi times x minus 3/4. And the rest of it I really don't care about. Y minus 1 equals 4 pi x minus 3 pi, and then I add 1. So that's the tangent line. Yes?
I'm sorry, can you go back a little bit? Where did the negative 2 come from?
Oh, secant of 3 pi over 4 is negative rad 2, and it's squared, so that becomes, then it becomes positive 2. Shit. Thank you. Yeah, because it's squared.
Oh, okay.
Yeah, that's my bad. So that's a negative 4, that's a negative 4, that's a negative 4. That is a plus 3 pi. Okay, thank you. Okay, let me see. Oh, this class does go through 10:20, so too bad. I've been so spoiling you guys. Yeah, even further. I spoiled you guys so much, so it's too bad. You guys are just going to have to deal with it. I want to talk a little bit about the next section's idea. Okay. Somebody help me out. Real quick. What is the derivative of of this. Nice. Come on.
Y prime.
There we go.
14x.
Okay.
What happened? 7 moves to the front, yes.
-1. 28x to the 6th.
Times for everything inside of this 2. Yep, so 42 is
I love you guys so much. I still haven't heard the right answer.
I said 14x to the 6th.
I know you did. So it's wrong, isn't it?
Yeah.
Wrong?
It totally is wrong. Why is 28x to the 6th wrong? Also. Because how many 2's do I have? 6 of them. Shit.
Oh, okay. Yeah,
Okay. All right, stay with me now. That wasn't supposed to be the hard part. Okay. Sorry, guys. How do I do this? This derivative, what would I do?
7 sin x. Times for everything inside. 6 times for everything inside. Cosine.
All right, let's just, I don't even care about the rest. Well, how about this? I'm sure you guys are going to catch on here eventually. What do you got, Jeff? I don't know, man. If. All right, how would I take this guy's derivative?
7 times that to the 6th times the derivative of that.
Yeah.
All right, so the first, all of these are basically the same, isn't it? They're all something. So if I have y is a function of x to the 7th power, right? How would I take this guy's derivative? The 7 would come out front.
Yep.
It's now to a 6th power times f prime of x, yes? Okay, so what we're able to do now, believe it or not, is I can do, let's see, something not too freaky, Jeff. Yeah, okay. I can take this guy's derivative. Can you solve that for y?
Yeah.
Oh man, teach me. Okay,
I'm going to say sine.
I was going to say,
So you can differentiate.
the teacher becomes the student. Show me. That you can't really. There's no real way to solve that for y because it's not a function. Right? If you try to graph this thing, it'll be kind of spirally kind of thing going on. How do I take this guy's derivative then? What's the derivative of y? Y prime. Yes?
Yeah.
What's the derivative of x? 1. What's the derivative of sine of something? This is just like the thing that was changing. This could be y, this could be y, this could be y.
Cosine y prime.
Cosine thing times
Oh, times y prime.
y prime. Shit! That's a chain rule, isn't it?
Yeah.
What is y? It's a function of x. We just don't know what it is because we can't solve for y, but I can take its derivative anyway. So we're expanding beyond functions. We can now do derivatives of things that aren't functions. And you're like, I didn't want to do that. Too bad. And then how do I solve this? How do I figure out what y prime is?
Divide.
I'm going to subtract y prime. I like it. Then factor it out. And then divide. Yes? So y prime will be 1 over cosine y. Can you guys still see that? Yes. Pretty funkadelic. So next time I'll have some graphs for us to look at, right? Because we can graph these even if they're not functions. And we're going to do some tangent line shit. And we're going to see that it does exactly like we expect it to. This is something called implicit differentiation. These are all explicit. I explicitly tell you what the function is. Here, do you know explicitly what y is? We don't have a freaking clue. So of course we call this implicit differentiation. Okay, that's enough. Sorry. I just want to throw something new in at the end. All right, guys. Let me know if you have any questions. Otherwise, I'll see you guys Wednesday. Yeah.